so maybe you found a link to Paczynski paper from 1986 on the wiki. And actually, it discusses the observation of machos, and it discusses the window for possible black holes or whatever. So, and it's very readable paper. So if you're interested, click on that link, and it will give you whatever you need to know about machos. That's first. Second, I put a new link to this Nobel Prize in 2011 physics. So again, you can click on that, and you can read about the three guys who got it, and you can read. So it was awarded for this discovery of accelerated expansion of the universe. Okay, so it's just regarding the wiki. By the way, yesterday you asked me about the cold dark matter. So we have lambda CDM model. So this CDM, the cold dark matter, doesn't stand for what is the theory for the dark matter, but it rather stands for the fact that dark matter is now cold. So it's non-relativistic dark matter we observe. Okay. So anyway, yesterday we started discussing dark energy, and so it was already realized in the 80s that if there is no lambda, then actually the cosmological prediction for the age of the universe is very wrong, because the universe would be younger than some observed objects in the universe, and that of course would be trouble, because if they were created before the universe was here, then we are in trouble. Okay, so that was sort of one evidence that there must be lambda, but really the overwhelming evidence is this Nobel Prize in 2011, and so let me just reproduce this calculation, and so you will finish it in your homework, and then we will all get Nobel Prize. So, okay, so. And that supernova type of the supernova observations. It's Nobel Prize 2011. And so the physics behind this is all very, very simple. So basically what they did is that they did distance versus redshift measurement. So all it is distance versus redshift measurement. And so they did that measurement, and what they observe is, well, okay, so this depends on the model, as we will discuss in a minute. And the truth is that the luminosity distance is larger if you have lambda present. And so this is what precisely was observed. So luminous distance is larger if lambda present. Okay, and so that's all that measurement basically showed. Okay, so let's do the theory behind this. So let us assume that we have FRW, and let me use these coordinates. So ds square is a square of eta minus d eta square plus d chi square plus sk square of chi d omega square. Okay, and so let us calculate and observe flux, which comes from, to us from a source with luminosity L. So this luminosity L is assumed to be known. It's some standard candle. In our case, the supernova thing. So the picture, so you want to calculate, observe flux. Flux is usually denoted by F from a source with luminosity L. And this will be located quite far, so located at some co-moving distance from us, chi m, located at chi m, like emitted light. Okay, so we are sitting at chi equal to 0, and you know, this thing is sitting at chi m, and it's sending photons to us. So the picture is something like this. You have a star. Well, it's like a sea star. I don't know. So anyway, and so this star is sending to us photons everywhere. Okay. So now, let's say that it emits some shell. Well, in some time it emits some shell, and that shell we observe here. Okay. So the area of this shell, well, from the metric, it's just that the omega part of the metric, right? So it's 4 pi. Now, if we observe it now, it's A0 square, and then sk square. So that's the area of the shell as we observe it now, as it actually reached us. Okay, and let's say that this shell has, well, L shell, which is A0 times delta chi. So now I'm interested in the radial distance, so it's A0 times delta chi. And because I'm taking that C is 1, this is equal to basically the time, how long it takes for the shell to, you know, from the very beginning till the very end. So it's delta T shell. It's how long it lasts. And that's A0 delta eta. Okay. So let's say, okay, so this is all clear, I think. So now let us assume that, you know, this shell was emitted at this delta eta time. So within delta eta, so the energy which was emitted is just luminosity times the time which it takes to emit that, but the time is related to my delta eta is A times delta eta, so it's L times A delta eta at the time when this was emitted. Okay, so this is very simple. So this is the energy. Now remember that everything which comes to us is redshifted. So we have that the energy, which is proportional to the spatial part of the momentum, is proportional to 1 over A. So that's what we derived a long time ago. So that means that delta E observed, well, the energy is redshifted with respect to the emitted energy by this factor. So it's delta E emitted, and now A over A0. So A0 is now A when it was emitted. So this is just redshift. And if I plug in for delta emitted there, this is just L A square delta eta A0. Okay, so far so very easy, right? It gets even easier later on. Okay, so now this is the observed energy, but we are not interested in the observed energy, we are interested in the observed flux. So, okay, so observed flux F so flux is energy per time per area. Okay, so it's delta E observed divided by how long it takes. I denoted by delta T shell, and per area, and the area is the area of the shell. Okay, so that's the observed flux. So now if you plug whatever we calculated for delta E observe, then this is equal to, and whatever the S shell is, 4 pi A0 square SK square. So this is equal to L over 4 pi A square A0 to power 4 SK square, and this is at emitted time. Okay, so that's the observed flux. So far, so easy, right? So now the last step in the calculation, and we are done, is to, well, at this point, this is a function of this chi emitted, but you want rather this to be a function of the redshift, which you can measure, right? So you need to rewrite this as a function of z. So want to rewrite this as function of z of the redshift. So how this is done is very simple. So you know that the ratio of the scale factor because of the redshift is equal to the inverse ratio of the frequencies. Okay, so now I add one and then subtract one. So I put minus omega 0 and plus omega 0. So this thing is z, and this is just plus 1. So this is equal to z plus 1. Okay, so now I can find what is dz. So let's differentiate this guy. So dz, and let's take here. So of course, d of 1 is 0. So I have that this is equal to minus a0 a square dA. And I can write dA as dA over dt dt. So now, so I have a dot, and then I borrow one of the a's here, and I get h. So it's minus a0 over a h dt. Okay. Okay, so that's what dz is. So now, you know, the light is coming as an incoming null geodesic, so I have incoming null geodesic. That means that d eta is minus d chi. So as the radius is, well, the radius is decreasing because the geodesic is coming towards me. Okay, so then we have, so all we have to do is basically we have to evaluate this chi emitted as a function of z, and then we are done. So let's do it. So chi emitted as a function of z. So what it is, so first of all, an identity. It's just emitted to now d chi. So now chi is equal to 0. So chi ras is equal to 0. So this is definitely true. Now, using this thing, the minus disappears and it's plus. So it's emitted 0 d eta. Now I use the definition of eta in terms of t. Emitted 0 dt over at. So I continue that line, but however, I know how to write dt over a from that dz formula. So dt over a is something like dz over h over a0 and minus sign. So this is equal to, now to destroy the minus sign, I just swap the limits of that. So now I'll be from 0 to z, and then 1 over a0 dz prime h z prime. Okay, I'm just using what that dz is. Okay, so we are done. So we now know, so we have the formula for flux, which is this formula here. And you just plug whatever the chi emitted in that sk square is as a function of z here. So this is just whatever you observe. So of course now I need to, the last thing I have to do is I have to express this h as a function of z. But for that I have the Friedmann equation. So I have h squared equals to something. So h squared equals to 8 pi g Newton over 3 rho total. And then you know that this rho total is a sum of over all possible components in the universe. So particularly if you have one component, then rho I is proportional to what we derived a long time ago, minus 3, 1 plus wi. So that comes from the continuity equation. Right? So this is where this is p over rho. Right? So now I have to sum over all these possible rho i's. So this guy actually equals to, so now I can always write rho I over rho 0, and then there will be a0 correspondingly here. And that a0 I can take out, so I can write h0 here. So anyway, the result is obvious. It's h0 squared sum over I. Now omega I is just rho I over rho critical, and then 1 plus z, 3, 1 plus pi, this thing here. Okay, it's just really writing this thing over there. Okay, and that's it. So this is the Nobel Prize calculation, right? So you just shuffle, this thing with that to here, and you have the flux. And then you want to measure that flux. So now what people don't usually like flux on its own. They like other quantities. So people like instead of flux, they sometimes are interested in luminosity distance. Which you define as if you were in a flat space. So you know that the luminosity sort of decreases with, well, luminosity is fixed, but the flux decreases with 1 over L squared. So that's precisely how we define that. So dl is L over 4 pi f. And so these people like, or they like magnitudes, which are quite often used in astrophysics, and in particular apparent magnitude. And that comes from the fact that your eye is a logarithmic device. So it sees the things 2 times brighter if there are actually 10 times more photons coming to. So that's why this logarithmic thing. So m is minus, I don't know where 2.5 comes from, logarithm of 10 of the flux. And that's the apparent magnitude, and that's apparently what your eye likes. And so this is what people will sort of plot. So they will either plot the luminosity distance as a function of z, or they will plot apparent magnitude as a function of z. And if you do it, and you will do it in your homework, is that then you get a graph something like this. So this is your apparent magnitude. This is your z. And now we can, this you measure. Well, this is my unknown, which I'm plotting with respect to this. But these are the parameters, basically. So the omega i's you can play with, right? And so you can play with, so by setting omega I, well, all of them 0, and taking, for example, omega lambda equal to 1, then you have just dark energy dominated universe. If you put all the matter, then you will have just matter, and then you have some you know. So then you can plot these things, and you get various graphs, right? So you get something like this, something like that, something like that, for different values of the choice of omega of your parameters. So these correspond to different cosmological models, meaning different omega i's. Okay, and so you may be plotting these things, and at some point you choose that omega matter is 0.3 and omega lambda is 0.7. Okay, so let's say this is this line here. So it's omega lambda is 0.7 and omega matter is 0.3. And so if this were true, then this line would be true. And then, of course, then you have to actually measure the magnitude with respect to z for a given object. And this is precisely what these guys did. And they find, that this line, well, of course, it doesn't fit that nicely, but that's the one actually selected by observation. Right? So, for example, this one would have, I don't know, omega lambda equal to 1 and omega matter equal to 0 or something like that. This would be something else. But this observation uniquely fixes what your matter content or what your content of the universe is. And that's it. So that's the Nobel Prize. It's beautiful, right? It's very, very simple calculation. And so all I want you to do in your homework is basically take that formula for flux, plug in this formula and play with whatever this omega are and plot it, right? And select the correct universe. Right. So yeah. So usually, people choose some absolute magnitude, which is like brightness of a star at one parsec or whatever. I don't know. So there's always like a fraction. So you would take m1 minus m2, and then there would be flux coming from that, and it would be comparing to some reference star if you want. Yeah. But you're absolutely right. There should be. So people measure, difference in magnitudes, not these things. Okay. So this is an overwhelming evidence, which is now accepted as a proof that the universe actually has lambda, and it's actually exponentially. Well, it's accelerating expansion. So there are, however, other observations which I'm not going to mention, but they are sort of independent observations to this one. Well, independent. They are not really independent. So these are, for example, I'm not going to talk about these at all. Baryon acoustic oscillations. Of course, CMB, we have seen that it provides independent check of the matter of the content of the universe, B-cleansing. And so they all agree exactly on this content, omega lambda 0.7, omega matter 0.3. Okay, which is amazing. But in some sense, it's not that amazing as it looks. They are not really independent measurements. What they really are, all of these things are measurements of a distance. And so all of them can carry the same mistake, right? So this is very important to realize that all these are in fact distance measurements. So they can all carry the same mistake, same error. Okay, so let me just. Well, this is all very simple, right, and very nice. So now cosmological constant problem, let me just mention it again. As I said, we have an old one, which I already mentioned. And that's if you know that vacuum fluctuations should contribute to lambda. I said that. So what is observed is rho lambda. Again, it's something like 10 to minus 29 gram per centimeter cube. So that is the energy density of this all-penetrating vacuum energy. And so if you write it in Planck units, and this is 10 to minus 120 in Planck units. So this is an observation, but QFT gives you that the vacuum fluctuations they have the right structure, but they should be of the order. So the Planck density should be, well, m Planck to the power 4, while in the Planck units, m Planck is 1, so they should be of the order 1, right? So rho vacuum is m Planck to the power 4, which is 0.1. So we are off by 120 magnitudes. Okay, so. Okay, so that's a problem. Well, you measure sort of vacuum energy by, for example, the Casimir force or whatever. So I don't know what's going on. Nobody knows what's going on. So that's the old problem, right? So that you know that the vacuum fluctuations should contribute, they should gravitate, but if they were really gravitating, then the energy density would be much, much bigger, and we wouldn't have any universe, right? So something, have to save our universe, so that rho lambda is much, much smaller than predicted by QFT. Okay, so now the new cosmological constant problem. I never understood why it is a problem, but so basically, if you remember that graph, so I had a logarithm of A, logarithm of rho, and so you have, well, maybe inflation, but doesn't matter. So now I have the radiation goes like with the slope -4, and then you have matter, which goes with the slope -3, and then you have lambda, which goes with slope 0. So this is lambda contribution. So now we are somewhere here. So we are already in this lambda dominated part. But in some sense, why we live so close to this point? So that's the new cosmological constant. So in other words, why again the value of lambda is such that we are close to this crossover? So why this is interesting? So why the question is why we live so close to the equality between lambda dominated and matter dominated era. So this question seems stupid. Why not? Right? But the problem is that in which era you are, the structure formation behaves differently. So you can show that if lambda were, for example, a little bit bigger, and that means we would be living further away from that matter dominated, then actually the structure formation wouldn't occur, and we wouldn't see universe as we see it now. So this is related to the fact why we see universe as we see it, basically, and this is called anthropic principle. well, one possible explanation is anthropic principle for this problem due to Weinberg. And so anthropic principle basically says, well, we see universe as it is because we see it, right? So it's just like a tautological thing, but you know, basically you are saying, well, if the universe would look completely differently, then there would be nobody to observe it, basically, right? So because we can observe it, it must have all these fine-tuned things and so on, so that what we see is possible. Of course, it doesn't explain anything, but people like this anthropic principle, and it sort of makes sense, right? So if there were, you know, I don't know, billions and billions of universes, only those actually who are appropriate for life would you know, sort of, there would be like clever beings observing those universes, right? So this is anthropic principle, and it's an argument, you know, which can solve this new cosmological constant problem. Are you happy with that explanation, or not really? So anthropic principle is basically saying a universe is as is because we can observe it. Of course, many physicists don't like this principle. Yeah?
Is it obvious that rho lambda should be rho vacuum?
No. So rho lambda is something which is observed at this point, right?
Yeah,
so this is, you know, something which is given by observation,
yeah.
right? But what I haven't shown you, but what is true, is that rho vacuum, well, that the vacuum fluctuations, they have precisely the form of lambda. And we know that the vacuum fluctuations should be there because we trust our QFT, right? So it's been verified a lot. So you trust QFT, and so you measure the vacuum energy by Casimir effect and so on, right? So you believe that these vacuum fluctuations are there. So now we calculate, you know, how much energy density they contribute, and they would contribute this energy density based on some, you know, rough estimate. Right, so this should definitely contribute to lambda, right? But if it does, then there must be some other miracle which actually cancels the contribution of vacuum fluctuations by something else, so that in the end we observe just this. So there must be some miraculous cancellation. It's not a perfect cancellation because otherwise lambda would be 0, right? But it's nearly perfect cancellation. Or maybe this is wrong. Yeah, exactly. Thanks. Yeah, so wise. Very good. So the last thing here I want to mention about dark energy is this non-cosmological constant problem. So we have cosmological constant problem, and then we have cosmological. So cosmological constant problem, and we have cosmological non-constant problem. And I won't say much about it. I'll just give you the reference. And it's actually Naeshafskhordi and Nelson, who is a postdoc here. So our faculty and postdoc, and it's archive 1504 00012. So if you are interested. And basically, you know, what is the idea of this paper is that, well, I have these vacuum fluctuations and they must be present. So basically the T mu nu, the corresponding energy momentum tensor of these vacuum fluctuations. So what it does is it influences the metric, right? So it influences this homogeneous FRW geometry. Okay, so we have the vacuum fluctuations, I take the average value of the T mu nu, and that actually determines how my space-time looks in these large scales. However, you know, because these are vacuum fluctuations, if you go to quantum theory, then you may have high order correlators of T mu nu, right? So you may have, for example, T mu nu vacuum and T alpha beta vacuum, or higher order correlators of these things, and they should sort of influence. So these are should influence higher order classical statistics of cosmological perturbations. Statistics of cosmological perturbations. Okay, so basically this guy is our lambda, or contributes to lambda, and then, you know, it's the homogeneous part which is affected by that. But then you also have, you know, tiny fluctuations around these homogeneous things. So for example, me or you, we have fluctuations over these things, right? But now, because T mu nu is so big, right, then this guy will be even bigger, right? And so these fluctuations actually should be huge. We don't observe that either, right? So you know, this is even, you know, more severe, because if this guy goes like 100 to, well, 20, then this guy goes much more, right? And so the inhomogeneities which should be produced by these fluctuations, by these higher order correlations, should be huge. Moreover, you know, I can sort of claim here that I can tune the energy level, sort of that, you know, maybe I choose the energy level somehow that this is approximately energy equal to 0 or something like that. But here you cannot, right? Because this is something which is there. So that's a cosmological non-constant problem, and talk to Naesh if you are interested more. But I think this is very, you know, convincing and severe argument, which is even more severe than the old cosmological constant, right? Why don't we see these guys affecting our inhomogeneities, basically? Questions? So Naesh was awarded some prize for this. So it's a good stuff. Oh no. But we started late, right? So what I would like to do now is I would like to at least start a little bit about inflation. So far we've been discussing basically, you know, physics which is very well grounded. So now we are moving to the realms where actually, you know, this is a little bit speculation, but it's actually very well motivated speculation, if you want. And so it's sort of accepted up to some people that actually inflation did occur. Okay, so that was part F. So part G, inflation. But you have to admit that there are, you know, alternatives to inflation. This is just, you know, one possibility. And so before I tell you the definition of inflation, let me just talk a little bit about co-moving horizon, co-moving Hubble horizon or radius. So you know that, you know, FRW space, basically you have two length scales. So one of them, so FRW has two length scales. So one of them is given by the Hubble expansion rate. So it's a Hubble radius. Of course, C is 1, so you know, I can always turn something, you know, to have appropriate units. So C is 1, so Hubble radius is 1 over h, which has units of time, but yeah, I can put C. And then the other one is the radius of spatial curvature, which is if I have my slices of t equal to constant, they have this radius a. Okay, that's my a. So this is in units where actually so where I set this rho equal to 1. So this is the radius of spatial curvature a. So now the ratio of these two things is what is called Hubble radius, co-moving Hubble radius. So you define r hat to be the ratio of, so this is 1 and the other 1. Okay, so this is equal to 1 over a dot. And that's the definition of co-moving Hubble radius. It's a dot here. Sometimes it's also called co-moving Hubble sphere. Or co-moving Hubble volume. All these terms are used for this guy. Okay, so here's just the ratio of Hubble radius divided by radius of the spatial curvature. Okay, so now why this quantity is interesting? So it tells us, first of all, it tells us whether the expansion of the universe is decelerating or accelerating. So if you have decelerating expansion, which means that a double dot is smaller than 0. Well, if you look at this definition here, so that means that the Hubble co-moving radius is actually increasing. Okay, or dr over dt is bigger than 0. If you have accelerated expansion, and it's the other way around. So the co-moving radius is going down. So now, what is the physical meaning of this r hat? And I'll try to convince you that it's a co-moving distance within which the particles can immediately interact, sort of. Okay, so I have, if I consider a physical distance, this is just a motivation. Okay, so physical distance is just c times, and so let's say that the particles, well, that the light can travel this physical distance within 1 Hubble time. Okay, so th. So this is the physical distance a light can travel. Light can travel in Hubble time. But remember, the Hubble time is a time in which the scale factor in which the universe sort of expands twice, right? So I just remind you, I already wrote this guy, that th, which is h minus 1, is dt over the log of a. So basically, this is a time in which the scale factor doubles. Okay, scale factor doubles. Okay, so that's what th is. That's the time in which the scale factor doubles. And then, you're asking, how much, what is the physical distance the light can travel in this time? Okay, so this is equal to, well, c is 1, so I forget about that. And then th, well, is just a times delta chi. So that's my scale factor, and that is the co-moving distance, right? So this is what it is. So in other words, I say that this is precisely r hat. Well, this is what it is. So r hat is 1 over a and then th, right? So r hat, the meaning of r hat, is really a co-moving distance. The particle can travel here and now, basically in time when the universe expands twice. Okay, so that's the meaning. So what it actually tells you is, whether the particles can communicate now, sort of within, this short time th. Right? So you can sort of say, so it tells you about, possibility to communicate here and now. So let chi be a co-moving separation, of two particles, then if chi is bigger than chi of particle horizon, so review what a particle horizon is, but basically I'm saying, well, remember, particle horizon is something at a given eta. So I'm sitting at chi equal to 0, and then chi particle horizon is the distance, from where things could actually affect me. So if chi is bigger than that, so it's sitting over here, it could never have affected me, right? So if chi is bigger than that, particles could never have communicated and if chi is bigger than r hat, it means they cannot talk to each other now. So basically, this r hat tells you, which particles, which part of the universe is in causal contact now, and which is not. Okay, so this r hat very important for causality. Okay, is this clear? Maybe just go through the derivation motivation. So anyway, so r hat tells you about causal contact. Now, okay, so that's the definition of the, well, if you don't like this explanation, don't worry. Just remember that r hat is defined in this way, is the ratio of the two scales, and that whenever you have decelerating, it's actually increasing. Whenever you have accelerating universe, it's decreasing. Okay, so now I have to at least give you the definition of inflation. So inflation well, the theory of inflation postulates that the radiation era was preceded by an era of accelerated expansion. So That means that if you want, you can define an expansion, the inflation as a time where this co-moving Hubble radius was actually decreasing, which of course is the same as a double dot. Okay, so your Hubble radius is decreasing. Co-moving Hubble radius is decreasing. So now, in order this inflation to work very nicely, this had to happen very, very rapidly. So in the first 10 to minus something seconds, your universe had to expand like crazy. So it had to, boom in no time. Okay, and so for that, so during inflation, our hat shrinks like crazy. And so people define, well, okay. So if you take our hat initial at the time when the inflation started, and you compare it to our hat at the time when it actually finished, so this is defined to be e to the n. So exponentially, you had to shrink your co-moving horizon, and this n is called number of e-folds. It's called number of e-folds. Okay. Question? No. No question. Okay. So really, this happens very, very rapidly, and it really the size of the universe, becomes much, much larger, exponentially larger what happened before in no time, basically. And there's this exponential. So now I'll discuss, not today, but tomorrow, I'll discuss 3 puzzles which actually motivated, the definition of inflation, or motivated the theory of inflation. And to solve these puzzles, just to give you a ballpark, so to solve puzzles which you don't know yet, well, you know one of them. You know the horizon problem. To solve puzzles, which I'll mention next time, you need n to be something like 40 to 60. So really, your universe had to expand very, very rapidly. And so let me start with these puzzles next time. But from what I'm saying you here, it's obvious that we don't really have a theory of inflation, right? It's obvious that it's just a framework for theories. It's not a unique theory. It's just, this is what I need in order to solve puzzles, right? But how this is physically done, of course, there are some proposals, but it's not. It's just a framework for various theories. It's not one theory. It's just all set of theories which can give you this.
But the notion that it happened, is that like a consensus thing right
No.
now? Or?
No. So we are here in speculative physics, basically, right? But it's very efficient to solve very many interesting puzzles, and so that's why people mostly accept it. But of course, there are counter proposals and there are alternatives. And so for example, Neil has different theory than inflation, and it has different predictions for certain things. So for example, when people measured gravitational waves coming from inflation, well, he was saying, well, this cannot be true because his theory doesn't predict those, right? So, but yeah, it makes sense, right? Okay, so let me mention these puzzles and let me proceed with inflation tomorrow.